In this section, we'll look at vectors and vector equations. So a matrix with only one column is called a column vector. And so when we write it, it looks like that. Oftentimes, textbooks write it as a, like if we have x, y, z, they might write it as x, y, z with a little transpose, or sometimes they leave that off. Again, when we think about a vector, we think about a column vector, but it's a little bit ambiguous sometimes, so always feel free to ask. The notation is usually a bold-faced letter or the letter with the arrow over top. I try to use the arrow over top because I can't bold my writing. And then we think about if we have all, x, y pairs, that is in R2. If you have all x, y, z coordinates, that's R3. So the exponent, if you want to say it, in top of the R tells you how many components there are to the vector. U is an example of an element in R2. So this symbol right here means element of. So this phrase means the vector v is an element of R2. V is also in R2. W1, W2, W3 is in R, like this vector is in R3, and each of the entries is in R. Put R1, but you don't usually put the 1 because they're just real numbers. X, this one has 4 components, so that's an element of R4. So we can visualize vectors in R2 and R3, but we cannot draw them in the higher dimensions. So here are some visualization of some vectors in R2. We have the xy plane, and we have a graph of u and v. And we're asked to label and sketch negative u, 2v, u plus v, and u minus v. So let's start with negative u. So when you have a negative u, we're just going to go in the opposite direction. So right now, u goes 1, 2, 3, 4, 5, up 2. So it goes over 5, up 2. So we're going to go left and down 2. So that is negative u. If I want to do 2v, that is doubling the size. So I'm just going to double the size. So that vector, this entire one, is 2v. If I want to add u plus v, we call it the head to tail method. So I'm going to kind of pick up this v and put it at the end of u, and the vector from 0 out to that point is u plus v. Then finally, if I have u minus v, it's going to be u plus the negative v. So negative v is this. And so if I do the head to tail method, you can put either one. So I'm going to transform this, put it over here. And that means the vector from the origin to that is u minus v. So that's kind of a visual description of adding and subtracting and multiplying by a scalar with vectors. Algebraically, it works just like you'd expect it to work. So a scalar times a vector, you're just going to bring that scalar in to both components. If I want to do 3u minus 2v, I'm going to bring the scalars in first. So I have 9, negative 12, not plus, but minus 2, 10. And then you do component-wise. So 9 minus 2 is 7. Negative 12 minus 10 is negative 22. And then u plus v, I skipped that one. They are both in R2, so I can add them. So I get 4, 1. Looking at some more operations algebraically, we have vectors u, v, and w. They are all in R2 because they have two components. And I want to think about, how does u plus v compare to v plus u? Does it matter what order I add them in? In other words, are the vectors commutative? And the answer is yes. And that's because when you add them component-wise, they are just real numbers, and real numbers are commutative. Is it ambiguous to write u minus 3v plus 8w? Do you know which operation to do first? Our order of operations defined. And they are really the same. It's exactly how you expect them to work. So are parentheses needed in this case? No, they are not. What vector could be added to v to get v back? And we don't want to write 0 plus v equals v. You need to have this vector line over that because it really means the 0 vector, not just the number. And does anything change if you are in Rn? It's still true that the 0 vector plus v1, v2, v3 is equal to v1, v2, v3. And when you write that, it's implied that the 0 vector in this case would have 3 zeros in it. Otherwise, you can't add them. So all these things, like it's commutative, parentheses are not needed, the 0 vector can be added to keep it the same. So all those are true for any vectors in Rn, not just R2. With this lattice, we're going to look at linear combinations of two vectors. So here's my v, and so the question is, can I add those two vectors together, some multiple of those together, to get to this point A? Well, I could go 1u and then a negative v and a negative v. So I could go 1u and negative 2v, and I'd get there. Well, what about another one? To get to the z, I could go 1v, a negative u, 1v, negative u, 1v, negative u, 1v. So I went 1, 2, 3, 4. So I went 4 v's and negative 3 u's. So to get to c, I could go 1, 2, 3 and a half. So 3.5 v's. And then a u and a u. So 2 u's. So the question is, could I get anywhere in this entire plane? So if I wanted to get to here, or here, or here, could I get to them any way? And the answer is yes. So because I can use fractions of u's and v's, I can get to any place in that plane. So linear combinations are critical for understanding this class. So given a list of vectors, we're going to call them v1, v2, up to v sub p, and scalars. So these scalars, c's, are real numbers. The y is called a linear combination if it is some constant times the vector, plus some constant times the vector, plus some constant times the vector. So those c's are called weights. And again, y is a linear combination of the v's, and the weights are the c's. So given that u is 1, negative 2, and v is negative 2, 3, give some examples of linear combinations. So again, some constant times the vector plus some constant times the vector. So you can pick any real numbers you want for those two spots. So if I make them both 0, that means it would, the vector 0, 0 is an example of linear combination. If I make both those coefficients 1, then I'd get negative 1, 1 is an example of a linear combination. If I make the first one 0 and the second one 1, that means negative 2, 3 is a linear combination. So using any weights you want, you can create linear combinations. If you're asked if a certain vector is a linear combination of the two, that means you're trying to find, what are my C1 plus C2 equals 7, 4. So are there weights, the C1s and C2s, that can work for that? And you can, spend some time just playing with that, or you can write it out as C1 plus 2C2 equals 7, and negative 2C1 plus 5C2 equals 4. And we know how to solve that, writing the coefficient or the augmented matrix. And if we row reduce this, you get 1, 0, 0, 1, 3, 2. That tells me my C1 is 3 and the C2 is 2. So let's see if that works. So 3 times, go through this. 3 times 1 is 3, plus 2 times 2 is 4. That does give me 7. And then 3 times my negative 2 is negative 6, plus 2 times 5 is 10. So that does give me 4. So it does work. So another critical word. So we just talked about linear combination. I'm going to say linear combination in the span. I hate to think about you guys counting how many times I will say both those words this semester. But the span of a set of vectors is the set of all linear combinations of those vectors. So in other words, if I want to describe the span of V is all linear combinations of the vector V. So if it's just one vector, it's just all multiples of that one vector. Span of UV would be the set of all linear combinations of U and V. All right, so here's some geometric descriptions. So this first one goes with this picture. So if V is a non-zero vector in R3, the span of V of one vector would just be all scalar multiples of that vector. And so if you think about that visually, it's just going to be a line in 3 space, and it's going to go through the vector V and through 0. So in this figure, the black bold is the vector V, and then the blue is just an extension of that vector, and that's the span of V because it represents every single point on that line. Now if I want to think about the second one, this is the span of U and V. So if U and V are not multiples of each other, that means the span of them is going to create a plane. So it's just a plane in 3 space. It's going to go through both U and V and 0. And it's just going to be a plane in R3, not all of R3. So if I want to give a geometric description of span of V1 and V2, where I'm given values for V1 and V2, I'm in R3. I only have 2 vectors. It's going to be a plane, and it's a plane in R3 because they are in R3. It's going to go through the origin, and it's parallel to vectors that you're given. And we don't need that. We just looked at vectors and how they are represented. Now I want to look at systems of equations and how we can write them as vector equations. This system has 3 equations and 3 unknowns. So I'm going to write this as a vector equation. So I'm going to look at each equation and find the coefficient of my x1. So my coefficient of x1 is here, here. So I have 1, 2. There is not 1 in the third equation. The coefficients of x2, there's not 1 in the first one. It's 2 and then 1. And the x3s are negative 3, 9, 5. And all that equals the vector 8, 7, negative 2. So it's going to be very helpful to be able to go from the system of equations into the vector equation. This entire equation is the vector equation, and then also going from the vector equation to the augmented system. So being able to convert between those three forms will be very, very helpful. This last example, we want to determine whether or not B is a linear combination of A1, A2, and A3. So just going back to what the definition of linear combination is. So linear combination means, are there weights, we happen to call them C1. So C1 times 1, negative 2, 2, plus C2 times 0, 5, 5, plus C3 times 2, 0, 8, equals negative 5, 11, negative 7. So asking, is B a linear combination of those, is asking, are there weights C1, C2, C3, so that this vector equation is true. And then we would solve this way we've been solving things. Write it in a augmented system. Row reduce it. When you reduce this, at some point you'll see 0, 0, 0, 3, and that's a big indicator that we have no solution. So is B a linear combination of A1, A2, A3? No. So there are no C1, C2, C3. There are no weights that will produce the vector negative 5, 11, negative 7.